Hi AP Stats. Today we're going to continue on with Chapter 2, working with Section 2.2. Section 2.2 is about normal distributions, and our learning targets today are to use the 68, 95, 99.7 rule to estimate the proportion of values in a specified interval, or the value that corresponds to a given percentile in a normal distribution. We're going to find the proportion of values in a specified interval in a normal distribution using Table A or technology, or find the value that corresponds to a given percentile in a normal distribution using Table A or technology. So we've been talking about density curves, and the most famous density curve of all is normal curves. The distributions they describe are normal distributions, and they play a large part in statistics. So you can take a look here. I have an example of two normal curves. Each of our normal curves show the mean with our standard deviation. We can see that the larger the standard deviation, the fatter the curve is going to be. So the normal curves have several properties. All normal curves have the same overall shape, symmetric, single peak, and bell-shaped. Any specific normal curve is completely described by its mean, mu, and standard deviation, sigma. The mean is located at the center and is equal to the median. The standard deviation controls the spread of the normal curve. Normal curves with larger standard deviations are more spread out. It's important to note that the point at which the normal curve changes from concave down to concave up occurs one standard deviation from the mean. Because of this, we can estimate where one standard deviation is going to occur. This is called our point of inflection. So if you take a look up here, I've drawn that in for you. We can see where our curve is concave down and where it starts to change to concave up. And where it changes is our point of inflection, and we can estimate that to draw in our curve where one standard deviation would be. We can also take a look over here and see where that occurs as well. All right, so let's continue on. As we take a look below, the definition, a normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by its mean and standard deviation. The mean of the normal distribution is at the center of the symmetric normal curve and is equal to the median. The standard deviation is the distance from the center to the inflection points where the concavity changes on either side. We will abbreviate normal distribution with the mean of mu and a standard deviation as n, and then in parentheses we're going to put the mean, comma, standard deviation. We are going to use this notation, so it's definitely something you want to get familiar with. All right, so let's take a look at the next page. The 68, 95, 99.7 rule. In a normal distribution with a mean, mu, and a standard deviation, approximately 68% of observations will fall within one standard deviation of the mean. So we can see that over here. 34% would be within one standard deviation above, and 34% within one standard deviation below. Approximately 95% of the observations fall within two standard deviations of the mean. So you can also fill on your chart. That'll break down between 1 and 2 above would be about 13.5%, and 1 and 2 below would also be 13.5%. Approximately 99.7% of the observations fall within 3 standard deviations of the mean. So to add to 99.7%, that means between 2 and 3 above, we would have 2.35% fall between 2 and 3, and 2.35% fall between 2 and 3 below, leaving with 0.15% to fall below 3 standard deviations and 0.15% to fall above. So again, you might want to fill that in just to have that for reference. But you want to know 68% fall within 1, approximately 95% fall within 2, and approximately 99.7% fall within 3. So let's take a look at the example. And I should also say before we go on that this 68, 95, 99.7 rule only applies to a normal distribution. It does not apply to just any distribution. So that is a common error that's made on the AP exam, so make sure you pay attention to if it is a normal distribution or not. So in this example, it says, the mean batting average 432 Major League Baseball players in 2009 was .261 with a standard deviation of .034. Suppose that the distribution is exactly normal with a mean of 0.261 and a standard deviation of 0.034. So they tell us it's exactly normal, and we have our mean and we have our standard deviation. We can note that with a capital N, and we put our mean first, 0.261, and our standard deviation, 0.034. So when it is normal, we can write it with our normal notation. So it says sketch a normal density curve for this distribution and label the points that are 1, 2, and 3 standard deviations from the mean. Okay, so you're going to do your best to draw your bell-shaped curve. And when you do that, you're going to go ahead and you're going to fill in your mean. The mean we know is going to fall exactly in the middle. So we're going to label our mean, and it tells us that our mean is 0.261. Now, we need to go through and fill in 1, 2, and 3 standard deviations. So we're going to do our best to estimate where one standard deviation would be. We know it's at the point of inflection. And in this case, one standard deviation, they tell us, is 0.034. So we're going to go ahead and add 0.034 to 0.261, and that's going to bring us to 0.295. And then we're going to go out about another standard deviation to mark where 2 would be. So it'll be somewhere out here, 2 standard deviations, and we're going to add another standard deviation to that, 0.034. And when we do that, that should be 0.329. And then at 3 standard deviations, we're going to add that again, and it's going to be 0.363. Now, you're also going to want to go through and you're going to want to fill in your chart going the other way, where we're going to list 1 standard deviation below, find it for 2 standard deviations below, and 3 standard deviations below. And when you're going below, you use the negative sign. So we'll go ahead and just fill those in. And again, to get that, you're just going to subtract the standard deviation each time as you go to the left. So it's going to be 0.227, 0.193, and 0.159. So we went ahead, we sketched our normal density curve for this distribution. We labeled the points. Another thing you can do, you know that there's 68% that fall within 1, so you can put your 34% within 1 above and within 1 below. We know 95% is going to fall within 2. So if we subtract 95 from 68, we're left with 27, and we're going to split that up between these 2 pieces right here. So this one is going to be 13.5%. This one will be 13.5% as well. And we continue out. The next one will be 2.35%. And the last one is 0.15%. And we're going to fill that in on both sides. Okay, so there you go. There is part A. Now it says, what percent of batting averages are above 0.329? So if we take a look here, there's a couple of ways we can calculate this. Some students are going to say, okay, it's above 0.329, and if they had their curve filled out, they're going to say it's going to be 2.35% plus the 0.15%. And when you add that up, you get 2.5%. And that is one way you can do it. But we also take a look at 0.329 occurs at the second standard deviation. And here's what we know. Between the 2 standard deviations, 95% of our data fall within there. So we know that 5% of our data are going to fall within these outsides. And so to be above 2 standard deviations to the right, you're going to cut that 5% in half. And so some students are going to think, okay, I'm going to take 100 minus 95 to get the 5%, and I'm going to split up between the 2 sides, and I'm going to cut that in half. Half of 5% becomes 2.5%. So that is another way you can do that problem as well. What percent of batting averages are between 0.193 and 0.295? So again, take a look at your chart. Here's 0.193 and 0.295. Looking at your chart, I think the easiest way to do that is to go ahead and you're just going to add 68%, because you know 68% fall within the 1 plus the 13.5%. And when you add that together, it's going to equal 81.5%. Okay, so I'm pretty sure you saw that I'm not sure because I was looking down, but between 0.193 and 0.295. If we mark that off where that occurs, that's right here. We have our 68% plus our 13.5%. Okay, so the check understanding is something we are going to do in class tomorrow. So I'd like you to skip down to the next page, past the check understanding, and we're going to take a look at the standard normal distribution. The standard normal distribution is going to be related to the distribution of our z-scores. The standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. If a variable x has any normal distribution with a mean of mu and a standard deviation of sigma, then the standardized variable z, where we calculate our z-score, has a standard normal distribution. The standard normal distribution will also follow the 68, 95, and 99.7 rule. So we are going to be using table A to help us calculate proportions in a standard normal curve. So table A is going to be our standard normal table. And in this table, it's a table of areas under the normal curve. The table entry for each value z is the area under the curve to the left of z. So again, we need to make sure that when we're using the table, we realize we're looking at the area to the left of that z-score. So let's think about this. Here I said, what's the probability that you're going to choose the z-score that's less than 0.11? Okay, so we're going to take a look. What proportion of our curve is going to be less than 0.11 is basically what that's asking us. So what you should do is you should draw a curve. So we're going to just first do a real quick sketch of a curve. And to show it is for our standardized curve, we know our mean is equal to 0. And our first standard deviation is going to be right here. That's going to be at a value of 1 because we know that a standard deviation is equal to 1. So now the z-score that I'm going to take a look at is 0.11. So if I was one full standard deviation above the mean, that means I would have a z-score of 1 and I would end up right here. But the z-score that we're going to take a look at is 0.11, so we're just going to be slightly to the right of the mean, not very far. So I'm going to go ahead and I'm going to mark where that is. That'd be somewhere around right here. I'll draw a little arrow up here. That's going to be z is equal to 0.11. Now, what you do is you go ahead and you mark that in, and then you shade, because we want to figure out what percentage of area of our curve is to the left of that. Now, if we think about it logically, we are just right of the mean. The mean is equal to the median, so the mean is where the 50% point of our curve is. So we're going to make an estimate that we know that the area that's going to be less than the z-score of 0.11 is going to be just a little over 50%. So here's how we use our table A. Since I'm looking for 0.11, I go over here and I find where 0.1 is. And I know it's kind of light, so I'm going to go over it darker. There's 0.1, and then at the top, I'm going to match up where my hundredths place is 1 because that's what was in our hundredths place here. So that is right here. So we're going to go down and we're going to find in our table where the 2 points intersect. And if you go over it, it's 0.5438. Okay, so what we're going to see right here is that the area that is in here is equal to 0.5438, about 54.38%. So the proportion of the curve that is that has a z-score that is less than 0.11 is about 0.5438. So around 54.38% of our curve falls below the z-score of 0.111. Okay, so let's take a look at the last example here using our table. So you'll have the table that I've handed out to you, and you want to have that ready because you're going to be referencing that. And anytime you are doing these types of problems, you need to draw the picture to help you make sure that your answer is on track. And it's just part of the strategy so it will make more sense to you. Okay, so draw your pictures. That's going to be important on this. All right. So it says use table A to find the proportion of observations from the standard normal curve, from the standard normal distribution, given the following z values, draw a diagram for each. One of the things that we want to remember is because it's a standard normal distribution, we know that we're looking at the z-scores. So in the standard normal distribution, we want to remember that the mean is equal to 0 and that the standard deviation is equal to 1. So remember standard normal distribution. You're going to say the mean, mu, is equal to 0. And you're going to have your standard deviation, sigma, is going to be equal to 1. Okay. So it says find the area that's less than negative 1.25. So you're going to sketch your curve. You're going to put in, this is your z curve, so we'll label it our z curve. So that means we have a normal distribution of 0 with the mean of 0, standard deviation of 1. So we're going to put our mean is equal to 0 is right here. We know one standard deviation below would fall somewhere right here. So if we take a look here, this is going to be a little more than one standard deviation below. So it's going to be somewhere over here. So this would be negative 1.25. So it's a little more than 1. And we're going to shade everything to the left. Okay. So now you're going to pull out your table A. And you're going to find the side that has the negatives on it. So we're going to find our sides with negative 1.2. So I found my negative 1.2, and then you're going to go up to the top and you're going to find where the hundredths is 5, and you are going to come down and see where they meet. Negative 1.25, I'm going to slide up so you guys can see that. And if you did it correctly, it should meet at 0.1056. So this is going to be equal to 0.1056. That's what is in here. So if you think about that, that's not quite 11%, almost 10.56% of our area falls less than negative 0.125. Okay, so try the next one. We want to do less than, where z is equal to 0.81. So again, you sketch your normal curve. For your z-scores, we'll put a z down here to show that we're talking about the z-scores. We're going to put its normal, 0, 1. That's going to indicate to us that it is our standard normal curve. And we're going to fill in our mean is at 0. Now, this is a little bit less than one standard deviation. One standard deviation is going to fall here, so it's going to fall somewhere maybe right around here. And we'll put 0.81, and we're going to shade that in. And you're going to go over, and you're going to take a look at your table A, and you're going to find where 0.8 is. So here we are, we find our 0.8, and you're going to go to the top and you find your 0.1, and I'm going to switch hands here. So we go down and we see that that is 0.7910. So this is equal to 0.7910. I'm going to draw that picture there to show that about 79.1% of our area is less than the z-score of 0.81. Okay, so now what happens when we take a look and I say, find the area that's greater than z equals to 0.81. Now, the table is for the area that's everything to the left. It's the lower tail to the left of the z-score. So we're going to go ahead and we're going to mark that again. We have our normal distribution curve here for our standardized curve. It has a mean of 0, standard deviation of 1. We're going to plug that in here. We'll put a z to show that that's what we're talking about. Because our z-scores, there's our mean of 0. 0.81, we know from the previous problem, somewhere right around here. But now, we want to find everything to the right of it. Well, our table only gives us everything to the left of it. And when we did the last problem, we saw that 0.790 was to the left of it. So what we're going to do then is we're going to go ahead and subtract that area from 1. If we know 0.790 is over here to the left, to get to the right, 1 minus 0.7910 is equal to 0.2090. So that's what the answer is going to be, and that is what would be represented right here. Okay, let's go ahead, and for the last one, we're going to go ahead and try part D. Now we're going to sketch another curve, and we're going to put it all together. So we have a normal standardized curve with a mean of 0 and a standard deviation of 1. And we're going to mark off where z is equal to negative 0.125. We did that up here in the first one, so go ahead and mark that off. Let's put our mean in as well. All right, so negative 0.125 was somewhere right here. And then we also had 0.81, which we've just been dealing with for the past couple of problems. That's going to fall somewhere in here. And the question is, what percent falls in between there? Okay, so using our table, we found that when z was less than 0.81, looking at part B, when z was less than 0.81, everything to the left of 0.81 was equal to 0.7910. So when z was less than 0.81, I'm going to mark that on my paper right here. When z was less than that, that was equal to, what did we say, 0.7910. Okay, and then we're going to go ahead and we take a look here. Now, when z was less than, basically what we want to do is we want to get rid of, okay, well, we know everything to the left of here is 0.7910. Well, maybe we can get rid of this little piece right here, and we would subtract it from there, and we would have our final answer. So we would go and take a look at our table, and we would find when is z less than negative 1.25. Well, we already did that up here in step 1. When z is less than negative 1.25, we saw that it was 0.1056. So when z is less than negative 1.25, we had an area of 0.1056. So basically, we have everything here. Everything is to the left. Everything to the left of 0.81, and we're going to subtract from it what was left to the left of negative 0.125. So we're going to have 0.7910 minus 0.1056, and when we get that, we're going to end up with 0.6854. So when I look back to this curve, I see that between negative 0.125 and 0.81 is 0.6854. Okay, so we will take a look at this example again tomorrow in class, and we will learn how to use technology. So let's go down and take a look at the last question. It says, find the 90th percentile of a standard normal distribution, and we're going to use table A. So if we're looking at our standard normal distribution, we're looking at our standardized data values, which are z-scores, and we're finding the z-score that's going to have 90% of the data values at or below it. So when I would sketch my curve, I know that I would mark that z-score pretty far to the right because I want 90% of the area of my curve shaded in to the left of it. So we're going to use table A. When we used table A before, we were looking at the z-score and trying to find the area within the table. Well, now I know that I have 90, I'm looking for the area of 90%. So when you're given the area, you're going to look within the body of the table, and you're going to find the percentage that is closest to 90%, or in this case, just 0.9 is how we're going to say it. So you start to look through your table, and as we start to look through, we see we have 0.8997, and then it starts that the next one will fall to be 0.9015. Now both of those are close to 0.9, but 0.8997 is closer to 0.9 than 0.9015. So we're going to use this value to answer our question. So we go ahead and we go to the left of that table, and if we line up 0.8997 here and we go all the way to the left, we see that lines up with the 1.2. And then we go back to the 0.8997, we go up, it's 0.08. So the z-score that has that is approximately at the 90th percentile is going to be 1.28. So it'll be fairly close. It should be approximately 1.28. Tomorrow in class, we will show you how to use technology, and the technology will even give you a couple more decimal places. Okay, that's it for today. Thank you, AP Stats, and have a great night.